I want to show you how to color a transparent piece of plastic without adding anything to it. No dyes, paint, nothing except holes. But first we have to talk about light. Most people know that it's a form of electromagnetic radiation. But have you ever stopped to think about how strange that is? I mean, light is a combination of electric and magnetic fields. Electric fields, like the ones that make these balloons repel, and magnetic fields, like the ones that make these magnets attract. But how can you strip off the electric field from around charge and the magnetic field from around a magnet and combine those fields together so that they can propagate out through space at the speed of light? Well, the key is the electric and magnetic fields need to be continuously changing. And this is usually accomplished by wiggling some electrons. That creates these oscillating electric and magnetic fields that propagate out through space as an electromagnetic wave. So how big is a wavelength of visible light? Well, take a ruler and have a look at a millimeter. Imagine magnifying that millimeter so it's the size of a meter. Now divide that millimeter into 1,000. Or in other words, take a millimeter of a millimeter. And then divide that in half, and that is the wavelength of green light. Now granted, that is tiny, but my point is it's not that tiny. And nature has actually figured out a way to take advantage of the size of light. Have a look at this blue morpho butterfly.
What's really neat about the blue morpho is, it has this really blue, iridescent, shiny wings that nobody actually really knows why they are.
You don't think it's to attract a mate or something?
The leading theory that I've read is to let predators know, like birds, that, hey, you know me, I'm really fast and I move really well through the jungle, don't even bother.
That beautiful iridescent blue color isn't created by a pigment. No, the color of the blue morpho is created by the structure of its scales.
If we were to zoom in on this butterfly, we'd see all these little sort of gratings and holes within these gratings that trap the light and reflect out this blue. If we just kind of look at it direct into the light.
So we've taken away the light that was bouncing off the front.
Yeah, you can see that the blue goes away. And all you can see is really the background. In fact, that's because the wings are almost transparent. Without that light being able to reflect off of it, you don't get any blue.
Scientists like Clint are trying to create similar structures to be used as security devices on banknotes, bank cards, and tickets.
What you're looking at is just a thin, transparent piece of plastic, and we've punched little tiny holes. The holes are about 100 nanometers deep and 100 nanometers in diameter. Each little image that you see on there has about 500 million holes punched into it. And those holes create a three-dimensional kind of grating that allow for the light to reflect and refract out and create those brilliant colors.
The color is created in a similar way to the color of a soap film. If you carefully study a soap bubble, you'll find that you can't see all the colors of the rainbow in the soap film. All you can really see is cyan, magenta, and yellow. Well, the reason for that is, what the soap film is doing is it's actually removing colors from the light. So the full spectrum of visible light hits the film, but depending on the thickness of the soap layer, certain colors are removed. And so what we see is the spectrum of visible light minus a color that's been taken out. So for example, in order to see magenta, what we need to do is remove the green light from the spectrum. The light that bounces off the front surface will interfere with the light that bounces off the back surface of that soap film. So when it comes out, any light that's about 500 nanometers is removed from the light, and what we see is a mixture of the rest of the spectrum. So longer wavelengths than green and shorter wavelengths than green, together they make that beautiful magenta color.
So what you want to look for is structures that are similar but can be compatible with manufacturing processes where, for example, a printing press process where you have a big roll of substrate, it's going to come along and you've got a big press that's just going to stamp down and punch in those structures.
But how could you create like nanoscale structures and punch them into a material? Isn't that nearly impossible?
No, not at all.
But it sounds like you're going to manufacture these tiny things and then they're not going to break off when you're stamping them in.
No, and that's one thing everybody thinks is oh well, they're small and small things are fragile. Well, that's just not the case. One of the reasons that our structures can be strong is that it has a low aspect ratio, which means that the height to width is low. So a high aspect ratio, let's say, might be 10 to 1, so it's long and skinny. And that is a weak structure. Ideally, you want a structure that's 1 to 1 or maybe 1 to 2. And what we do is we create structures that are 200 nanometers wide and maybe 400 nanometers tall. And we use that to punch in. And those structures are really, really strong.
For the moment, Australian bills are made of plastic, and they have this little transparent window in them to stop counterfeiters. But perhaps in future, they'll have hundreds of millions of tiny nanoscale holes instead.
The Australians were the ones that invented the polymer banknote.
So would you be looking to get your technology in there? Have you been in dialogue with the Australians?
I cannot comment on that.